Slide closed. Good afternoon. So I'm Dr. K.C. Varik. So today we'll start the second module of this course of Advanced Material Chemistry. So I'll mainly take characterization techniques for advanced materials. So today we will cover the basic concept. See, all characterization techniques, it depends on the interaction of radiation. It may be X-ray or it may be neutron interaction or electron interaction with matter. So that interaction of material with this radiation with matter is important for all these characterization techniques. So if you see, if advanced material, that advanced material, if you see that mainly the properties that will decide whether a material, you can say it's an advanced material or it's a normal material. And that properties, it depends on two factors. One is your structure of the material and another is the morphology. So structure driven as well as morphology driven, that the two parameters that will control the material properties. And to identify that material properties, we have to go for its characterization. So we need advanced techniques to characterize those developed materials, and because that properties or performance of the material, that will be strongly depend on the structure and morphology. If you see engineered material with engineered properties that we created through the development of specialized process or synthesis methods, that you can call as advanced material. And we need that better understanding of that materials through both nanoscopic as a microscopic states where we need these characterization techniques. So that you can divide the whole characterization part of a material into two things, two aspects. One will be your structural characterization, another is your morphology or interface characteristics. So if you see the structure characterization, those information you can identify from using either diffraction techniques or scattering techniques. So the diffraction and scattering, you can see that the scattering is the both terminology where diffraction is a part, like subset of that scattering, but only Bragg's law satisfies. So then only you will see a diffraction. Otherwise, all diffractions are scattering. So this diffraction techniques, which I will cover mainly X-ray diffraction, electron diffraction, and neutron diffraction. At the same time, the two scattering technique that we will cover in this module, that is X-ray scattering technique, that is small angle X-ray scattering technique, and small angle neutron scattering techniques. So if you see the morphology part or the interface part, so that interface characteristic, you can see either interface analysis, you can use the technique like X-ray photoelectron spectroscopy, X-ray absorption spectroscopy, or secondary ion mass spectroscopy. So those are some surface techniques, so they can identify the chemical states of the material, or you can identify its coordination number by using that X-ray absorption spectroscopy. But the imaging techniques that mostly use electron microscopic technique, like scanning electron microscope SEM, or transmission electron microscope TM, or even AFM atomic force microscopy or scanning tunneling microscopy. So those microscopic techniques are used to know about structural information, like especially in the morphology, as well as how it shapes and what is the topography of the material. So those type of information you will get. And all this characterization, as I told, it depends on the interaction of radiation, that is photon, electron, and neutron with matter. If you see X-ray diffraction or X-ray scattering, so or XPS or X-ray absorption spectroscopy, all these technique depends on the interaction of the phonon with that of matter of your samples. Similarly, all electron techniques like electron diffraction or scanning electron microscope, tunneling microscope. So those techniques will depend on interaction of electron with the matter. Similarly, with the neutron, that neutron diffraction or neutron scattering, that's all depends on the how the neutron interact with the materials, and then how it gives the different characteristics. So before going into all these characterization techniques, today we'll discuss in briefly how these three things, that that is photon, electron, and neutron that interact with the matter. So first, if you come into the interaction, before going into this, we can see how does light interact with the matter. If you see the light, it interact with the matter mainly in three different ways. So if you have a light incoming beam is here, H nu is coming and falling on the material, so then there is a possibility that three phenomena will occur. That one will be the absorption, that incoming beam can be completely absorbed inside this, or it can be scattered, or it can be transmitted. If it is completely absorbed, so there will be no transmission or scattering. But if it is scattering, that scattering can be different types. It can create generate different species like photoemission, fluorescence, phosphorescence, so elastic or inelastic scattering, or other electron can be produced. If incoming beam can be transmitted, we see that transmission electron microscope depends on this transmission phenomenon. So this thing, the process, and that there is nothing that complete absorption is quite difficult. So there is a terminology called attenuation. That attenuation is nothing but scattering plus absorption, both summation of both of that incident light beam can be considered as a combination of scattering and absorption. That means if an incident ray I0 is falling on the material, and then that beam that is transmitted, that I will be intensity of that I will be I0 into e to the power minus mu x. This mu is nothing but this attenuation, linear attenuation coefficient. So you can write in the mass in the term of mass or absorption coefficient. So if you divide by mass here, mu by rho and rho x, so you get that equation. So if you see a material is that it is a 90% is the attenuation capability. If the 100% intensity is coming inside here, so after first attenuation, it will 90% will be transmitted. Then after second attenuation, it goes to 81%, like so on. So by each step, the light beam will be that intensity will be attenuated depending upon the this attenuation coefficient, how your material is it has the capability of scattering as well as absorbing the light. So similarly to the light interaction, the radiation also interact with matter. So the interaction of photon, electron, or neutron as the transfers are mainly stochastic behavior, and it obeys laws of chance. Like it's not that there is 100% there will be interaction. So it's all based on a laws of chance, and it's very with a different behavior. So if you see that between these three, the photon is generally have a very few interactions, and it's an exponentially attenuated, and mostly it will be absorbed or scattered. So it will be interaction is very few, and photon interaction are expressed mainly in terms of cross sections of individual interaction. So that in the material, what is the cross sectional area where it interacts. So that and the attenuation coefficient of the material through which it passes. And if you see the electron, that electron experience large number of interaction. In general, is after interaction, the electron loses energy slowly, and it till they completely stops. So that means it depends upon that how the electron has the capability to move inside the material. That it's called as electron range. That up to what range electron can be propagated inside the material, and then the material stopping power. If the material is you can say hard or some very good stopping power, then electron propagation will be less. So mainly, but it has a large number of interactions that electron will come. And but it is similar, it is a comparison to photon and electron. Your neutron interaction, is a very low probability, because neutron is a very small size of the nucleus in relation to the atom. Because of small, that nucleus is a very small size in comparison to the atom. Because of that, the neutron interaction is very, very low. If you see here that if your atom is here, like it has a lots of the whole atom itself is there, then you can see the electron beam is coming here, and that electron beam can be scattered, or it can interact with the material. It can be like the electron scattering that will be either elastic or inelastic scattering is possible. And similarly in X-ray, there will be electromagnetic interaction will be there. At the same time, you have a X-ray scattering is possible. This X-ray will come, and on the top surface there will be the electrons will be there in the outer shell. So from the electron, it will so immediately it can be scattered or it can interact with them. But if you go to the neutron, so neutron has in addition to the neutron interaction, it has it has a magnetic interaction too. That means the neutron has a magnetic moment. Because of that, the neutron can interact with the nuclear interaction is possible. In addition to that, nuclear scattering, as well as dipole interaction, that is nothing but magnetic interaction or magnetic scattering is possible in case of neutron, which is not there in case of X-ray, and electron. So if one by one we'll go to all these different types of interaction. So first, coming into interaction of X-rays with material. So if you see that how that X-ray, when it falls on some material, the incident X-ray, so that incident X-ray fall on the material, so it will create a lot of interaction. Because of that, you will get many signals or emissions or various effects you observe. So first of all, if you see, if a X-ray is falling on a specimen, because of that X-ray, so you can see your material is getting heated up. So that X-ray energy can be absorbed by the material, and you will see some heat or some IR radiation is there. That is one possible. Then that from the specimen there can be a scattered X-ray, the X-ray beam which falling on the material. So after falling, it can be scattered at different angle. And this scattering can be two types. One will be coherent scattering, and another will be a incoherent scattering. That is coherent mainly from the bound charges of that specimen. But incoherent, where you will see mostly Compton modified interaction, or from the loosely bound charges were there. From there, the scattering is possible. So in addition to the scattering, X-ray can also produce some fluorescent X-rays. So because of that incident X-ray, that molecule, that material which you have, so that can even, fluoresce, and you will be able to get an fluorescent X-rays. Similarly, that X-ray can produce, some electrons. So you can able to see that Compton recoil electrons. You can generate photoelectrons simply. That incident X-ray will observe, and that will be that energy is sufficient to overcome that binding energy of that electron. So to knock out the electron, you will be able to see the photoelectrons here. In addition, you can also get transmitted beams, that X-ray beam which you are producing, some part of it can be also transmitted. So X-ray is mainly follows fluorescence, scattering, as well as electron interaction, as well as some heat can be produced. In addition to that, some very little amount of refraction or reflected X-ray can be produced if your angle of incident is very, very low. So if it's a very low angle, like 5 to 10 degrees or below that, you'll be able to see some sort of refraction or reflection. But otherwise, it's mainly scattering, or it's a nuclear or electronic interaction that you'll be able to see. So if you see the X-ray interaction, as I told, so there will be mainly two types of interaction. One will be elastic interaction, that is called coherent scattering, or inelastic scattering, incoherent scattering. When there is an elastic scattering, so the incident photon, if you have a wavelength of lambda I, it interact with the that material, and after that interaction, that lambda f, that wavelength of that energy which is emitting after interacting, so that will be same. So lambda I incident and final lambda f will be same. So that means in this process, you will see if it is elastic scattering, no electron will be ejected. There will be no production of an additional electron. There will be no energy transfer takes place here. So whatever the lambda I, that will be equal to lambda f, and there is no ionization process. That means that the incoming X-ray photon is substantially less than the binding energy of electron. If that lambda of that is that the energy is higher than the binding energy, then only that electron can come out. But since that in case of elastic scattering, the energy is very, very less, so in that case there will be no change change in the direction of the no change, it doesn't go any type of, change in direction without any wavelength change. So this interaction mainly occurs when you have very, very low energy X-rays like 15 to 30 keV. So these coherent scatterings that you see, if you see the example X-ray diffraction analysis, the XRD pattern, if you see, you may see some, high background in case of some of the studies, the analysis that the background radiation is mainly because of this coherent scattering. So that will be thermal diffuse scattering due to some defects inside the materials, or scattering due to pinhole, slit, or binder that you are using in the sample preparation, or the slit width that you are varying during measurement. So or then air scattering. So those type of scattering, mainly elastic scattering or coherent scattering, that only gives rise to background radiation. So the inelastic scattering, that is called Compton scattering. So that scattering mainly occurs when incident photon is deflected from its original path by interaction with the electron. So if you have a incident beam is going like this, and you have a photon is going like this, and you have an electron here, and this photon interact with this electron, and because of that interaction, so electron, you can see it deviates from its path. Instead of going in this direction, now it's deviated its path, and because of that you can see the original path is having changed because of incoherent interaction. The electron that ejected from the orbital position, or the X-ray photon that lost to the interaction, it's continuously travel through the material without changing their path. You can see that electron is moving this way, and whatever the lambda is incident after that scattered photon will deviate and it go in another direction. And the energy change depends on the angle of the scattering. This how much scattered angle is there, not on the nature of the scattering media. So here the scattered X-ray photon has less energy. This photon, scattered X-ray photon has less energy, and it has longer wavelength than that penetrating photon. That means that h nu you are here, that lambda f, so that will be higher than that of incident photon in the case of Compton scattering. Yes. So in Compton scattering, that means that since there is a change of position, you can see that because of this collision, there is kinetic energy conservation. Which here, this kinetic energy will be the h nu of the photon, that incident photon minus h nu of the scattered photon. So that here, in case of incoherent scattering, that does not contribute to the diffraction. It only darkens the background of the diffraction pattern. You see that, from the diffraction pattern of the electron diffraction pattern or X-ray diffraction pattern, so that means that the background will be darkened because of this. And since there is no fixed phase relation here in case of the Compton scattering, so that cross-sectional absorption is directly proportional to the free that for electron Z dependence. There is no Z dependence here, Z to the power 0 here. So it's directly proportional to the electron density here. So in this case, so if there is a dense material, your the Compton scattering will be higher. In case of light material, your scattering will be less. So another phenomena that takes place in case of X-ray photon interaction with the material is photoelectric effect. So if you see the photoelectric effect, that incident X-ray photon, it falls on the material that from the inner orbital, and because of this X-ray photon that is falling on the material, that one electron is you can see one electron is coming out from this orbital. So that electron here is producing is called photoelectron is here. So if this photoelectron will produce, if your energy of the X-ray photon it's more than that, is higher than that of the binding energy of that particular electron. So this electron here that was bound with the nucleus through some binding energy. So if the X-ray photon energy, that kinetic, that the electric energy h nu we are providing here, if that h nu is greater than the binding energy of this electron, then only this electron will be knocked out from this as a photoelectron. And because of this electron coming out, many processes is occurring here. So because this is photo, once the photoelectron coming out, so there will be a vacant site will be created here. And because of this vacant site, so you can different phenomena, there is X-ray fluorescence can be possible, or emission of a photon can be possible. You can see here this higher, this electron can jump to here, that excess electron energy can come out. So even able to see the electron production, you can see the fluorescence. So different phenomena will be takes place. So this photoelectron, that the energy of the photoelectron will be incident photon, that h nu, that so this is the energy of that photoelectron is equal to incident photon minus that binding energy. So this photoelectric effect, it's mainly predominant when you have a low energy photon, but that should be higher than the binding energy of the electrons. So then only you will able to see this photoelectric effect. And it's for high jet material, so the photoelectron production will be higher. So probability of interaction here is directly proportional to the Z, that is Z to the power 4, and inversely proportional to the energy of that, incident photon into the power 3. So this photoelectron will be produced when you have you can overcome the binding energy. The incident photon has binding energy higher than that, you'll be able to see the production of the photoelectron. So another phenomenon that occurs during that phonon interaction is called pair production. So that pair production means that you have a photon will converted to two particles, either a energy of a mass, that is electron and positron. So if I X-ray photon here, so that photon, if you instead of coming close to the near to the atomic nucleus, so that photon will interact with the Coulombic field, that the Coulombic field of the nuclear Coulombic field inside here. So the X-ray photon will interact with this, and then you will able to, that X-ray photon will split into that gamma, or X-ray will split into electron and positron. And to create these two particles, your minimum energy requirement should be 1.02 MeV. And that excess kinetic, that photon energy is given to the particle as a kinetic energy. Because of that kinetic energy, so this electron and positron, that will be keep on moving from the point of creation to a far away. And this then they will go to undergo many interaction, and still they lose their energy. So there will be many charge particle interactions possible. As pair production mainly occurs here, you can see the pair production which is occurring inside this Coulombic field of that nucleus. So it's mainly depend upon the nuclear charge, that Z square. It will depend upon the Z square of this particular material. And this photon interaction, if you see the three things that is coming, one is photoelectron effect and Compton and the pair production. So photoelectric effect, we see there's the water molecule inside that interaction of X-ray photon. This photoelectric effect is mainly predominant, when energy is, very low energy site, it is really predominant. But in between, you will see Compton effect, and for pair production, you need quite high energy of 1.02 MeV. And most of the material, if you see, the curve, nature of the curve will be remain like, it will be like same, it will go like this and this and this. But because there is a side shifting in that it's by energy position, but overall, the spectrum will be remain same. So in addition to these three, photoelectric effect, Compton effect, and pair production, the photo disintegration is also possible. That is direct interaction of electromagnetic photon with the observed nuclei. So in this will be possible photo disintegration if a threshold energy much higher than or equivalent to 8 MeV. That the 2 with 2 is possible. Only two exceptions, like for deuterium, it's 2.22 mega electron volt MeV, or in beryllium it should be 1.67. For all other case material, it should be more than or equivalent to 8 MeV. So because of the photo integration, that photon that will be observed, that will be interact with the material, and nucleus emits photons, like it's a gamma in case of X-ray, or gamma photon or gamma neutron is possible here. So these are the mainly how does X-ray interacts with the material, and because of this X-ray interaction, we will discuss how that photoelectric effect will give rise us to X-ray photoelectron spectroscopy for analysis of chemical state, oxidation state of a material. And similarly, if you have a Compton interaction, that will how does it contribute to the background radiation. And if you have a pair production, that you can see positron annihilation spectroscopy, so that is coming from that pair production phenomena. So from the X-ray, there will be X-ray scattering technique, X-ray diffraction techniques, so that all will come from the interaction of the X-ray or gamma ray with the materials. Similarly, electron also interact with the material in different ways. If you see interaction of electron with matter, so you can see here, so that mainly electron is a negatively charged particle, that mass and charge we all know. So it's you can see if an incident electron beam, and this is just sample substrate here, and electron beam is falling here. So because of the electron beam here, you will see different type of interaction. So this electron beam can propagate inside this material till a certain volume. So that is called this volume. So that will be called interaction volume. So up to this, that it can be penetrated. That is the range, that electron range till up to which distance it can propagate inside the material. So once that electron beam falls on the material, so because of that, whether it can be coherent or it's incoherent, that if it's coherent, that all you can see all phase are in same position. Incoherent, they are in destructive interference, you can see here. So this incident beam, either coherent or incoherent, that the electron beam when fall on the material. So because of this, that there can be a second electron production is possible. There can be some X-rays can be produced. A Auger electron can be produced, or some inelastic or elastic scattering can also be observed. You see, if that incident electron beam is observed, is coming here. So after interacting that, some of this energy will be lost as X-ray fluorescence or X-ray things. Or this electron can be returned back after interacting the material. That will be a backscatter electron, or this electron can be absorbed inside this material, and another electron coming out of that material. So that will be a secondary electron. So these are the different types of phenomena that can be possible, or even that electron beam can transmit it to this. So where that from the transmission electron beam, we'll see transmission electron microscope we'll discuss, and that whatever that secondary electron or backscatter electron is producing here, from that we'll discuss about how scanning electron microscopy uses these two electrons, and if this X-ray is coming out, so that you will use as a EDAX, EDX, energy dispersive X-ray analysis, or from there you can see the compositional analysis of the material, or if there is an Auger electron is coming out of that, so from that Auger electron or X-ray photoelectron, you can able to see that this technique, how it used to determine the oxidation states and other things. So this interaction of electron is also that you can say collision will be either elastic as well as inelastic, both ways possible. With elastic collision, there will no energy is transferred from electron to the sample, but in case of inelastic collision, there will be a transfer of energy. So electron penetrate once this you can see here, this is the nucleus here, and this is the electron, the surrounding here. So you can see the electron is coming here. So after going inside, so it interact with the Coulombic field of that nucleus. So because of this Coulombic interaction, the electron will change its path. So if you come very, very close to this, so it can be returned back in this pathway, like those are called, backscattered electrons. So the closer the electron comes to the nucleus, higher is the scattering angle. You can see the scattering angle here theta, and here you can see is so high because of this coming closer to the nucleus. So that will be in such a way that that electron will return back as a backscattered electron. You will be able to see here. So the probability of that elastic interaction is mainly depends upon the atom number, that Z square. As heavier the atom, more is the positive charge there. So Z square value is higher. So because of that interaction, probability will be higher. And with electron energy, that if electron energy decreases, so it decreases with the electron energy. And in case of inelastic collision, the energy transfer takes place from the incident electron. You can see here that this is because of the electron energy E is coming here after interacting with the E minus W. So W is the energy here that has been transmitted to the material. So energy E minus W is present with the electron. So these energy loss happen gradually with the distance travel. So as long as it keep on moving, still it has the stopping potential, that stopping energy is not that high. So still that it will be migrated inside the material, and we will see the energy loss will be gradual. And it is dominated loss mechanism. So energy loss mechanism is mainly through this inelastic scattering. And that interaction procedure, here that causes, excitation, ionization is possible, whereas in case of elastic interaction, this is not there. And because of the inelastic collision, what do we see? We'll able to see that this electron beam is falling here, and that another electron is coming out. So that electron is called, second electron fraction. And you can see from here, because of this removal, so there will be some X-ray fluorescence emission, or you can see there will be Auger electron transition. We will discuss that later, how the Auger electrons are produced. So this high energy electrons of incident beams removes the electron from the inner cell. Mostly that inner cell electron is closely bound to the nucleus, so that gives more information than the loosely bound outer orbital electron. So that's why in case of X-ray photoelectron spectroscopy, we used to study the core electron things. So we'll discuss those later. And once that electron moves from here, so that hole will be generated. And this hole which can be filled by a higher electron jumping from higher orbital to this. So that will be, because of that, will cause some X-ray can be generated, or it can be, so because of this, some other Auger electron spectrum, the Auger electron can be generated. So the interaction, in addition to the elastic inelastic interaction, that interaction of electron in the material also occur. So a background radiation is there, that is called Bremsstrahlung emission. So electron beam emit background radiation due to the acceleration caused by the electrostatic field of atom. Like if electron is coming, once it coming close to the nucleus, so there is a Coulombic interaction. Because of that acceleration, that speed that electron is migrating or moving through the nucleus, it slows down, and because of that step by step slowing down of this electron, that acceleration speed is decreasing. So because of that acceleration, so you'll see some background radiation that is called Bremsstrahlung radiation or Bremsstrahlung emission. And this, in each Bremsstrahlung event, so the energy E generate a photon of W energy. You will see because of the radiation that lose W energy, each step it will lose. And this, in addition to this, that if you have positron that is penetrating inside the medium, so that can interact with this electron. That electron which is moving inside the material, you have a positron inside that material, so it will interact with that. So it will try to annihilate that electron, and positron will annihilate. It will form two photons, that two gamma will produce here. So occurs when kinetic energy of the positron is large. here, then the absorption energy. So you like based on that positron annihilation spectroscopy is based. So this whole thing, how does electron interact? What type of, whether it's a secondary electron generated, whether it's a backscatter electron or it is a Auger electron, all depends upon the energy of the incident electron beam, your material characteristic, as well as there's a terminology like interaction volume, that is the three-dimensional region inside the material up to which that scattering is occurring. Like that, if an electron is coming here, it's scattered like this in randomly inside this certain volume. So that three-dimensional region is called interaction volume, or simply you can say it's a single electron range. So in that range, that's mostly 0 to 5 micron, the maximum electron interaction. That also depends upon the incident energy, electron energy of the incident beams. So this electron range is thus simple value that useful, for rough comparison and scaling of various signal destructions. So depending upon the incident energy, so you will see the electron range, and the size, shape of the interaction volume depends upon the how the elastic or inelastic scattering that beam is coming and approaching to the material. You can see here, if you incident beam of low energy here, low kV, you can see it's interact with narrowly in this system. But if you high energy, if you see that low energy with low Z material, it looks like this, but it's high Z material, that it means dense material, or you can see that atomic number is high, you can see the penetration depth is less here, and but it's broadened. But similarly, if a high energy with low Z material, you can the interaction volume is quite high as compared to that of high Z. Yeah. So that interaction volume, that the electron range that is mainly looks like a hemisphere that is proportional to the e to the power 1.67 here. The specimen is assumed to be here, that is a flat specimen, you can assume, and the thickness thick enough to the opaque. So then only this electron beam will interact inside the material, and then it will produce different types of electrons. So if you see, we'll summarize that electron interaction. You can see here that electron beam is coming here, and this is the interaction volume, which is different interaction volume I have shown here. So from the top surface here up to a length of 1 nanometer or so, that mostly secondary electrons are produced here in this region, and Auger electrons are produced on the top surface here. So beyond that backscatter electron, you can see the backscatter electron is going little deeper and interacting with the material, then coming out. So between secondary electron and backscatter electron, so that if you see the chemical information, like the elemental analysis, mostly we do with this backscatter electron, because it's coming from inside the material after interacting. So then going inside, if you see, there will be X-ray analysis, that redox analysis is here, the characteristic X-ray is produced. So there you can use the redox analysis, or you can produce continuous X-ray background radiation, or then beyond that you will see some cathode luminescence there. So in addition to that, so there will be some electron, it will be transmitted here. So the transmitted electron, there will be elastic scattering, there will be inelastic. In case of inelastic, there will be energy change. From that energy change, so you will see that composition, band structure, you are able to information. That is, from the TM, you will see here the transmission beam, you will be able to see this particle size or the shape of the material, and this Auger electron here, the surface support is, and secondary electron and backscatter electron that you can use to find out the scanning of morphology of the material. And whatever the electron is transmitted, if there is some energy loss, from there electron energy loss spectroscopy is coming into picture. So there you can identify the bond state or composition. So we'll discuss all those techniques later on. So that backscatter electron that you produce here, the coefficient of the backscatter electron will depend upon the number of electron that the beam electron, the number of beam of electron incident on specimen, that NB, the number of backscattered electron. that is beam mirror, or you can express it in space of current also. The number of beam electron incident on the specimen, that is NB, and NBAC, the number of backscatter electrons. So if I apply some number of electron that not N, this is called coefficient. You can find out the backscatter coefficient, and it's all depend upon this tilt angle theta. If tilt angle is normal here, 90 degree, that is almost 0 degree tilt angle seen an incident normally. In that case, it will see that mostly backscattered will be maxima. But if the tilt angle will keep on increasing, like n phi equal to n cos phi, so that once decreasing from here to here to here, you will see that the backscatter electron density will be erased. Similarly, the secondary electron also lose, that I already discussed from the specimen after observing that some kinetic energy from the material, that if you overcome the binding energy, then the electron will come out with sufficient energy. So that electron will be a secondary electron, and that coefficient will be number of secondary electron NAC divided by the total number of incident you are applying. So the secondary electron can also generate another secondary electron, that will be low resolution. SC can produce backscattered as well as SC1, SC2, different type of secondary electron can be produced. And here that angle theta increases again, that because of increasing the tilt angle, your coefficient will again decreases. So from electron interaction, what we see, so how does these different types of electrons are coming out, whether it is X-ray, whether it is a photoelectron, or whether it is a from the X-ray fluorescence, in case of X-ray interaction, or in case of electron interaction, it is the backscatter electron, transmission electron, or secondary electron. So based on those techniques, those interactions, we see all electron microscope or surface techniques that we will study. So next we will discuss about interaction of neutron with the matter. So here we will take we'll take 2-3 minute break, and then we'll start this how this interaction of neutron with matter. Okay, we'll resume the classes now. So there was a question in the chat box that why H nu was subtracted in case of X-ray photoelectron, that whatever the energy H nu we are applying on the falling on the material, so that H nu is equivalent to the kinetic energy of the electron which is coming out and plus binding energy. So that photoelectron photon which will fall on the material, that should have sufficient energy to overcome the binding energy of the electron, core electron, and it plus to the kinetic energy of that material. So because of that, H nu is equal to binding energy plus kinetic energy. So that means your binding energy is equal to that, it will be your H nu minus kinetic energy, or you can see that this kinetic energy will be binding energy minus H nu. So now we'll discuss that interaction of neutron with the materials. So all these neutron techniques like neutron diffraction, we'll discuss neutron diffraction, we'll discuss small angle neutron scattering, and these two techniques mainly depends upon the interaction of the neutron with the materials. So like here in neutron study, mostly use a low Z material study. Like if you see small angle neutron scattering, if you want to see them some hydrogen or some property or something like that, so it can be possible by using neutron scattering studies. So here you see the neutron was first discovered by Chadwick, who won the Nobel Prize in 1935, and was made based on the conservation of mass. You can see this the beryllium, which is 4 and then 9, the mass is 9. You can see with interact with the helium, and you will be able to produce a carbon 12 with 1 neutron will be produced. And this neutron has some mass that is about 2,000 times of electron, and it has a nuclear magnetron. That is the electron, that neutron possesses that magnetic properties. So that mu n you will be able to see, and it's indirectly is a ionizing radiation is this. And this neutron is electrically neutral. They can undergo deep into the matter since there is no charge like this electron, and they can't go very close to the nucleus. Once it goes, it will be backscattered. So but being no charge, this neutron can go deeper inside the matter, and it will be microscopically magnetic. So this can show magnetism, and it can give that angstrom wavelength. Because of the wavelength is very, very low, you will be able to see that structure at angstrom level. That means it can give you both structure and dynamic property, the energy of the milli electron folds that can show motion. So there is a motion because of the energy of the milli electron range, and you have an angstrom wavelength that can show the structure. So you'll be able to see the structure and dynamic properties by using neutron. And randomly they are sensitive, they can show even hydrogen atoms. So if you see that the neutron, there are mainly 3 types of neutron that we see generally. That's one is thermal neutron, or the slow neutron, the energy is less than 0.05 electron volt, and there will be intermediate energy that is 0.5 electron volt, 0.5 electron volt, not 105, this is less than 0.5 electron volt is your slow neutron, then 0.5 to 10 keV, that will be your intermediate energy neutrons. And then if its energy is quite high, like greater than 10 keV, you'll be able to see that fast neutron. So this neutron obeys de Broglie equation, that is like lambda equal to h by p. So that means it has a particle characteristic also. So you have see this neutron, you can generally produce in mainly sources of neutron. If you see, that can be produced by nuclear fission reaction, the spontaneous fission reaction, or in a photonuclear interaction, or even nuclear neutron generator. So mostly in research reactor, you can see that chain reaction is there, that you always 1 neutron per fission will be keep on going on, but the continuous flow of the reactor will be able to produce neutron in the this fission step in the nuclear reactor, or it can be laser driven or a spallation technique. So there will be no chain reaction, only first operation will be there. So for every proton, you will be able to about 30 neutrons you can generate. So here, so you can see in case of fission that uranium you can slow neutron, you can krypton, or barium you can disintegrate two subnuclei and you can able to get neutrons. In spallation, you can see there is a internuclear cascade, or highly excited something will fall on this highly excited nucleus will be able to get here because of proton interaction here. So because of that, you'll be able to see that is spallation and neutron generation. And similarly, in laser-driven process, you can also produce this type of various type of neutron. So if you compare that neutron with X-ray, you can see that neutron here, you can see the brightness that is here 10 to the power 15 or in flux is 10 to the power 11 order. But in case of X-ray, you can see here it is the order of 10 to the power 10 here in that flux. And if you go to that X-ray generated in case of this wiggler or undulator like that, this in case of this synchrotron, so you'll be able to see here, you see that flux of that X-ray is quite high. Since the flux is very, very high here, even in a lesser time, you can able to get much more information. Your time requirement is less, your sample requirement is less, but neutron flux is being quite low. So these neutron experiments used to take quite longer time because of your fluxes is quite low. So so when you go for a neutron measurement, always like in case of X-ray, you can able to get X-ray spectra in 2 minutes or 5 minutes. You can get even good X-ray spectra. But in neutron, you have to keep on hours to get that equivalent spectra. So the neutron can interact with the matter with like bound neutron, and the nuclei are stable, but free neutron, so they are unstable. So they have very less lifetime, so they will try to interact with the other matter. So that during neutron interaction, there no charge, so it interact with the nucleus. So means that no charge can penetrate closer to the nucleus, and it can interact with it. And internuclear radius is about 10 to the power minus 30 centimeter. And nuclear force, the nuclear force leading to this interaction is very short range. And because of small size neutron in relation to the atom, and the probability of interaction is very low. So neutrons have long traveling distance than other things. So there's less interaction. So it can interact with electron via its magnetic moment. It can interact, and this interaction can be elastic and an interaction, inelastic and an dash interaction, or that electron can be absorbed, that can be captured, and it's a radiative capture if the gamma ray emission is there, or that neutron can undergoes fission reaction with heavy jet materials. If you see, the neutron has higher penetration depth in comparison to other. And these neutrons are scattered by the nucleus, not the electron. See, X-ray that the electron can interact with the electron, but this neutron will go inside and is scattered from the nuclei rather than electron, and they leave a portion of the energy until they're thermalized or absorbed. And neutron is quite sensitive, like slighter element like hydrogen, oxygen. You can see that micelles, vesicles, surfactants, organic molecule structures, protein structure by using this neutron diffraction and neutron scattering techniques, because all these organic matter is composed of carbon, hydrogen, and oxygen or nitrogen. So those type of material you can easily see by neutron diffraction. And the neutron, you can see different type of scattering is possible. There is elastic scattering is possible, or there is a inelastic scattering that can go to excited state, or there is a radiated, that is a gamma ray emission can be possible. That is one mass can be added to the neutron mass can be added to here, and you can get j plus 1 and x plus j, or it can be a radiative capture, that will be radiative capture in gamma ray production, or it can be a charged particle, proton, deuterium, or Hill alpha particle you can produce through this type of interaction, or that fission reaction it can be possible that I discussed. So if you come into one by one, that slow neutron mainly interact in the way of neutron that undergoes neutron capture. So if a slow neutron like a sodium-23, that neutron can be captured here, can produce a sodium-24 and a gamma ray emission is there. So this will be a N gamma reaction can be possible. Similarly, you can able to charge particle, electron, alpha, or photon can be produced. If there is gamma particle, it's called radiative capture, and probability of capture is inversely proportional to the energy of the neutron. That means that the energy, if it is very, very low, the capture will be high. So low energy, that higher capturing capability is there. And these are some of the neutron capture examples. Like radiative capture, you can see that hydrogen can capture one neutron, you can go to deuterium, and gamma ray can be produced. That is mainly used in dosimetry or shielding, and this hydrogen is major component of tissue, so it will produce radiation dosage to human also. It gives because of this and gamma reactions, and it can be there is cadmium that can be radiative capture that used in case of neutron shieldings because of this capturing capability. In boron that used as a nuclear power reactor is a controlled fission process. You can see that undergo that this alpha particle is produced, or charged particle you can produce. Similarly, charged particle can also produce with nitrogen. That will be this. Then here the proton is produced at neutron dosimetry. So all these type of N gamma, N alpha, or N P reaction can be possible in case of slow neutrons. But in addition to that, the slow nuclear neutron also cause fission of uranium-235. So that will be produced, that the fission plus few neutron can be produced. So the mean number of neutron will be around 2.5. So that will be available for further continue the you can capture the remaining neutron. Only one you can be allowed to control way proceed the chain reactions. So, but in case of fast reaction, so there it will be interaction in different way. So neutron interact with the particle of approximately same mass, such as proton, like this proton, like both are same mass. So that will be a billiard ball type interaction. Like both are equal mass, so they interact like a billiard ball. So material rich in hydrogen, like water, wax, concrete. So those type of material characteristics you plan to identify, we will go with the elastic scattering of the energy of using fast neutron. But after collide with the nucleus, neutron deflected in different directions and it loses its energy by and lose its energy. And the energy recoiling, that recoiling nucleus absorbed by the meteor. So you can see here the incoming neutron is coming here after absorption. So the neutron will be energy G dash, the remaining energy is absorbed by this nuclei, recoiling nuclei. So total energy is conserved in case of this elastic interaction. But if you see inelastic interaction, that neutron interact with the particle which much greater mass. In that case, neutron was interacting with the hydrogen atom. But here, if you see the neutron interacting with the iron, or it's like a ping pong ball striking a bowling ball, like a small ball striking a big one, you can see here. So here, the interaction is like, ping pong ball with striking ball. So energy transferred to the target nuclei in this case. So then the neutron will absorb by this nucleus, and then it will emit that neutron, and in addition to the gamma ray. So here that the energy transferred to the target nucleus, so nucleus will go to excited state, and then that emission will occur. So here nucleus left in excited state, by relaxing the gamma ray will produce in this case. So in this inelastic scattering, so primarily occur in high Z materials. So if you see the neutron interaction, by burn, the neutron will be a fast neutron. So after interaction, it will slow down to thermal neutron, and then finally it will go to the capture. You can see a 1 MeV neutron energy, it will be fast interaction, it's 100 keV, 10 keV and so on decrease. If the energy is lost to 0.025 eV, that will be where the neutron capture occurs. So mostly, so by birth, neutrons are highly, high energetic. So the probability of interaction of nuclear, as I discussed, is quite less because, it's a very small, tiny, as compared to nucleus is a very tiny comparison to the whole, atom. So probability of interaction of neutron with a given material is expressed in terms of neutron cross section. So that is a unit of that is 1, that is 10 to the minus 24 centimeter per centimeter square. So sigma, that is by the cross-sectional neutron cross-section number of scattered nuclei per second by incident flux. It depends upon how much the neutron scatter depending on the total of neutron flux you are applying. So it depends upon the nuclide as well as neutron energy. So total cross section, since you have a scattering is possible, you have a capturing is possible, and fission is possible, total cross section will be summation of all this. In a macroscopic way, in a microscopic way, if you see that n0 number of atoms are there, so it will be n0 into sigma, you will see. So that probability of that increase the probability of nuclear interaction, you need a moderator to lower the thermal velocity of the neutron. That then only you will see the higher neutron interaction. And this neutron interaction, like X-ray, that attenuation, the thing that if you see I equal to I0 e to the power minus x, so that here it depends upon that, that this mu, that coefficient itself depends upon that. So neutron loses energy as they interact with the matter, and that characterized by neutron, that the attenuation length, that so that it means the scattering length that depends, and neutron depends upon the isotope, but independent of that q vector, that is wave vector, in which that sine theta by lambda where that interaction occurs. So it's mainly that depends upon the isotopic mass. But if you see that X-ray case, you can see that it depends on sine theta by lambda. But you might have seen one case that in case of X-ray diffraction pattern, if you see the X-ray pattern, that intensity of the peak, that higher angle, if you go to higher angle, the intensity of the peak decreases. But in case of neutron diffraction, if you see that all the peaks are, the intensity of the peaks are randomly varies. Like in higher angle, you can see larger, high intense peak, and lower you can see the smaller peak. But in case of X-ray diffraction analysis, always that it follow, higher angle it decreases. That is because it depends upon the electronic interaction, that is scattering factor sine theta by lambda. In case of X-ray, it interacts with the electron, but in case of neutron, it interacts with the nucleus, and the nucleus that depends upon the scattering length of that interaction, neutron interaction. So that varies with randomly. So because of that that interaction, that peak intensity varies. So that we'll discuss, we'll individually discuss different techniques. So today, so far I have discussed, different radiation, like X-ray like photons, neutrons, as well as electrons, and how does they interact with the materials, and based on this interaction, how the different techniques, like from X-ray, we have X-ray diffraction techniques, small angle X-ray scattering, we have X-ray photoelectron spectroscopy, from electron, we have scanning electron microscopy, transmission electron microscopy, as well as we have Auger electron spectroscopy, or a secondary ion, that mass spectroscopy, that is separately different from this. So how these different techniques, and from neutron, we have a neutron diffraction and new small angle neutron scattering. So all these techniques we'll discuss in future classes in details. But today I'll just in next 20-25 minutes I will cover how the X-rays are produced and what are its characteristics. So first we'll touch on the X-ray techniques, then we'll go to the neutron diffraction techniques, then finally we'll go to the electron techniques. So if you see the X-rays are mainly discovered in 1895 by German scientist Röntgen, and that from the cathode ray experiments, that he was doing. And when he did this experiment, that he named it X-ray because that he was not known what it was. So X stands, he was unknown. The Rontgen observed that a new type of radiation, possibly due to the interaction of electron with the glass wall, that time he thought that could be detected outside the tube. And this could penetrate opaque substances, blacken a photographic films, and produce fluorescence, ionization gas. So that he named is a X-ray, X-ray. So the X-ray is defined as a weightless packet, doesn't have a weight, a pure energy with no electrical charges, and it travels in a wave along the straight line with a specific frequency and a speed. But it doesn't have a mass or weightless packet. You can see the properties that X-ray are broadly classified properties. It's a physical properties, it's a biological properties, you have a chemical, it's a physiochemical properties X-ray can show. Like we discuss individually, but you can see the electromagnetic spectrum, the X-ray here, so it has a shorter wavelength here that you tensor -9 to the -11, and the high energetic in the spectrum. If you see the physical properties, the X-ray belongs to a family of electromagnetic radiation having wavelength between 10 angstrom to 0.01 angstrom, and its travel speed is it's almost the speed of light in vacuum, and they are invisible to our eyes, and they can't be reflected or refracted, deflected by magnetic or electric field. Since they don't have a charge, they are pure energy with no mass, so you can call it a quanta or a photon of energy. So they can penetrate various objects and degrade them, and it depends on the quality of how the intensity of the X-ray beam and its wavelength. Depending upon that, it can damage the material properties. And it can also have, biological and chemical properties, like most of the organic compound, it can be bleached, like for methylene blue get bleached, a full green if of sodium plantinocyanide, it turns into dark green. So then finally it goes to brown color. So X-ray destroys, fermenting capabilities of enzymes also. So like some biological effects are there. So X-ray affects that photographic papers. You can visible the same way the visible light, and the X-ray excites the biological matters which are unable to take chemical processes. That normal state is they are not observed. When biological damage, it causes many biological damage because of X-ray. Then X-ray are transmitted through healthy tissue, but absorbed in the bone. So because of that, we are used that X-ray film. That X-ray is used as a medical diagnosis purpose, because inside our body, the bone, which is made up of mostly hydroxyapatite, that calcium is main constituent. So it can't be propagated high calcium, but tissue hydrogen is there, so it can be propagated there. So you'll see that because that bone structure or the on the photograph X-ray films. So these X-rays are mainly produced by the conversion of kinetic energy of electron into electromagnetic radiation. That kinetic energy of the X-ray is getting, the kinetic energy of the electron is getting converted to the electromagnetic radiation. You can see here, this is a cathode ray tube. Inside that you can see there is the target here, and copper anode is here. Now the copper anode, and you have this tungsten filament here. From the tungsten filament, electron will come and it will fall on the tungsten target here, and from this tungsten target, X-ray will be generated, and whole thing will be kept in a proper potential, so that the X-ray can be taken out. So mainly it's produced by striking of high electron beam on metal target. So for production of X-ray, you need an X-ray tube. So this is the X-ray tube that you need here. In the X-ray tube, you have a electron source that is here, that is tungsten filament, that is electron source. From the tungsten filament, it will fall on the cathode copper anode, that will be a target is here, X-ray generation. Then you have a electron acceleration potential will be there, sufficient potential inside that, so that can be come out. So cathode, that is electron source, and anode is the give you the acceleration potential, and you have a target device, a rotor or stator, and whole thing will be inside a vacuum, because that it has to be the all inside a vacuum it can be produced. So here that you can see here that electron released from the cathode, once the electron coming from the cathode, they are accelerated towards the anode, that is the copper target, with by the electrical potential difference. So there is a potential difference, so that because of that electropotential, the electron will be migrated towards the anode, and then when it falls on the anode, the energy loss of electron takes place. That energy, the kinetic energy electron, is produced, that X-ray along with some heat can be produced. The intensity of the electron beam decides the intensity of the X-ray. So the X-ray intensity depends upon that, the electron intensity. So about 99% of the kinetic energy will convert into heat. Only 1% or 0.5 to 1% electron energy only converted to X-ray. So less of the energy it goes as a heat produced, and this heat is produced, it's mainly because of that projectile electron which coming to the closer to the cathode, that anode, that targeting material. So that will interact with that projectile electron released from the cathode, interact with the outer shell electron of the target atoms. You see, these are the target atoms here. So each target atom, so there are some electrons. So the incoming electron, the projectile electron is coming for production of X-ray, so that will first interact with this electron. So because of this interaction with the outer shell electron, the outer shell electron goes to the excited state. So from the excited state, they immediately drop down to the ground state by radiation of IR, infrared radiation. But that infrared radiation is responsible for the production of the heat. So because of that heat, the 99% energy is getting lost, and only 1% or so we are getting the X-ray production, utilized for X-ray production. And because of this interaction of the electron on the target material, the anode, we are able to get two types of phenomena. That one is background radiation, that is called Bremsstraff lung, or you can get a characteristic radiation mechanism, that will be K alpha, K beta, or L alpha, L beta, those type of characteristic radiation. So the projectile electron interact with the inner shell electron of the target atom. That inner shell electron, you can see here that this electron, that projectile electron here. So that electron here, the project incident electron here is coming here, that is interacting with that inside the material, and because of that you can see that one electron is coming out. It's like photoelectron. So this electron is coming out from this the projectile electron. So once this electron is coming out, what is happening? So there is some vacant space is creating. So projectile electron with energy higher enough can totally remove from the inner shell. If this is overcome the binding energy, so this electron come out, and on-field shell is energetically unstable. Now it is a vacant shell that is unstable. So the outer shell electron here you can see, so that will be come inside to fill this vacant orbital, and because of that a characteristic X-ray will coming out from the material. So that characteristic X-ray bears the properties or the characteristic of that particular material, and it's a fingerprint for each material. So different material has different type of characteristic X-ray. You can see here, if you can K cell electron here, inner K cell electron is coming out, and that K cell electron is filling with L cell electron, that will be a K alpha. You can say it's a K alpha radiation. Or if it's from M cell, it's K beta, or N cell, you can say it's a K gamma radiation. Similarly, for M cell to L cell, or higher to L cell, it will be a L alpha, L beta, L gamma, or similarly in the M series, higher to M series, it will be M alpha, M beta. So the excess energy will be released as a characteristic X-ray during the transition. And this energy released is equal to the difference between the binding energy of the two electron state. Like here the electron, sorry, from here and here, that whatever that binding energy difference, so that energy released, so that energy is the characteristic phenomena. You can see from in addition to K alpha, K beta, K gamma, K alpha, that L cell has a 3, that L2S, 2P, 3/2, 2P, 1/2, that L1, L2, L3. From that you can say K alpha 1, K alpha 2, or some higher energy X-ray emission can be produced. So these X-ray, these characteristic X-ray are, characteristic to a particular element. Like for example, if you see that, tungsten, that these are the electron binding energy of common X-ray tube that use case tungsten, molybdenum, rhodium. They are used as in that X-ray, common X-ray tube. So here that for each whatever the X-ray is coming from the material, that K alpha, K beta will be corresponding to that particular material. So binding energy is that unique to a given element. Since each element has a particular binding energy, the emitted X-ray have a discrete energy that is also characteristic of that element. So K alpha or K beta which are getting, that is the characteristic to that particular element. So it depends upon binding energy proportional to Z square. So then you can see here that you have a K alpha, K beta, and K gamma will be produced. This is K alpha 2, and K beta is produced. So K beta, and in addition to that, you can see there is a background radiation here, and this background radiation is called nothing but your Bremsstrahlung radiation. And that you can see K alpha, they have a particular energy, and K alpha 2, they have a particular energy here. So these are characteristics to that particular element. So the characteristic X-ray, other than those generated by K-scale transition are unimportant mostly. So they are almost entirely attenuated within the X-ray tubes or filtered by using some filter. So mostly we are interested about only K-cell or the X-ray diffraction studies or any major source material in XPS or other X-ray, small angle X-ray technique. You can see here you have a K alpha 1, K alpha 2, K alpha 1 is highly intense. The ratio of the K alpha 1, K alpha 2, K alpha 2 to K beta is 6:3:1. You can see that's K beta. You can see here this K beta is there. Then you will get in X-ray spectra that the diffraction pattern you will see those you have to remove by using some filter. And that filter you choose Z-1 formula, that is molybdenum the target, molybdenum -1 atomic number, that zirconia. In case of copper, it is nickel, and so on. We use that in case of this filter to source out K beta. But K alpha and K alpha 1 and K alpha 2, it's in conventional X-ray, it's difficult to separate by using filter. But that can be eliminated if you use a highly monochromatic, energetic, and bright source like synchrotron radiation for this X-ray studies. So you have a short wavelength limit at lambda in the relation is at 120, that you have volt kV, that the voltage, whatever volt you are applying for the X-ray production, the wavelength you will get 12,1400 by 4 volt. That equation is there, and from the X-ray, that characteristic X-ray followed that Mosley law, that is mu to the power half equal to Z minus sigma. So to this, the characteristic X-ray is depends. In addition to the characteristic X-ray generation or background radiation, we also get some fluorescence things. That the X-ray, the fluorescence also possible. Like for example, if you take a copper source, the cobalt, iron, or manganese, they can give some fluorescence. So that means some atom absorb X-rays and it fluoresces them as a X-ray in different wavelength. Like the incident wavelength it's getting, that it can absorb and it radiate at a different wavelength. So that means they fluoresce in a different radiation wavelength. So in case of this cobalt, iron, and manganese, if you copper target, you go for X-ray diffraction pattern, you will see lot of background radiation because of the fluorescence. So in case if you take molybdenum or some other source, you will not get that. You will get a very nice spectra with less background. So depending upon your fluorescence material you choose, you can choose your target element to eliminate your background radiation. So that this I have already discussed, that Bremsstrahlung radiation, that during that positive electron, it interact with the different incoming radiation, interact the electron, and it slow down its speed. And because of the deceleration, the acceleration speed is decreasing. So some of the energy loses as a kinetic loss, energy losses. So that will produce Bremsstrahlung radiation, and we will able to get this strong background in addition to the this characteristic X-ray. So if you see that here, you can see that that mostly the background radiation that will mostly kV from 10 to 90 kV in that region. You'll see the X-rays of low energy with much greater abundance. You'll be able to see in this case. And Bremsstrahlung X-ray have a range of energy. You can see from 10 to 90. The average energy will say 1/3 here. That's about 40 or 45. In that you will get the highest X-ray energy spectrum here. And in this, you will be able to see your K alpha, K beta lines. So X-ray production efficiency mainly influenced by the atomic number, that Z of the element, as well as kinetic energy of the photoelectron that incident on this. So for this X-ray that mainly that produced by using these X-ray tubes, by using a high electron, that source where the electron is coming and falling on the anode, and X-rays are generating, and we are moving out through a high potential. So these X-rays are mainly huge. If you see the application, they can use in a security purpose. You can see in airport or cargo scanning, we use this X-ray for the scanning of the material based on atomic Z value. And in medical also, you can see the radiography, that our X-ray that we used to get upon different parts of our body, that X-ray film we use in medical purpose. But in analytical technique, which we will mainly discuss, the security and medical issue will not discuss. We'll mainly discuss the analytical technique. This X-ray is used in wide range of application, like in X-ray fluorescence spectroscopy. We can use these X-ray sources, and for depending upon the flow energy, time energy, or wavelength dispersive, WDS, or energy dispersive identification, we can chemical states in the chemical composition we can identify by using X-ray fluorescence spectroscopy. We can see for a zinc oxide sample whether zinc is there or not, how much percentage is there. That quantification can be possible by using a standard. But for XRF analysis, you always have a very good standard. If there is not good standard, your result will be lot of ambiguity in the result. Yeah? So that will be X-ray fluorescence spectroscopy will discuss, and in that how wavelength dispersive, that whatever the X-ray produced, so that will be differentiated by wavelength wise, or it can be by energy wise in energy dispersive spectroscopy. Then you have an analytical technique that we use in XPS, X-ray photoelectron spectroscopy. So that photoelectron spectroscopy can use to identify the oxidation state of the material, whether it is, for example, in copper oxide or copper sulfide, or the copper is in +1 state, +2 state. There is a, from the binding energy, though it is a very closely associated with each other, 1 or 2 electron, EV, 2 EV differentiate can be possible by using this XPA to identify what type of element is there, and which quantification can also be done by using X-ray photoelectron spectroscopy. And then we have X-ray diffraction technique, where you can do phase identification, crystal structure analysis, all those, the different, like, can see whether the successful structure is formed or not, how much impurity is there, whether it's crystalline, amorphous, those study you can do with XRD. And in the next class, we will discuss mainly X-ray diffraction technique first. In the X-ray diffraction technique, we will discuss about conventional X-rays, its sources, detectors, as well as its principle, some of the examples, its analysis, and how the root wheel analysis, and then how this interpretation of this carbon identification, as well as the particle size, crystallite size, strain, and how the different factors are affecting the X-ray diffraction pattern. And in addition to the thin film XRD, like grazing angle XRD, synchrotron XRD, small angle XRD, all those things we'll discuss in briefly in next two classes about X-ray diffraction techniques. So after the X-ray diffraction technique, we'll go to the other techniques. Okay, so today mainly we discuss these three techniques, that X-ray, electron, and neutron, and all this technique depends upon the interaction of this material X-ray, electron, and neutron with the matter. Based on the interaction, we discuss different techniques like XRD, TM, CM, or Newton diffraction and scattering. So we will discuss in detail individually in next class. So if there is any question, you can put here. So next class, I will give some of the books that you can refer for these courses. So if any question, you can put in the chat box. Okay, if there is no question, we can stop here, and I will see you on next week. Friday, on Friday we'll discuss the next part. Thank you.